In section 5.3, I'm going to discuss Newton's second law. Specifically, I'll introduce the second law of motion, explain how to calculate the weight of an object given its mass, and I'll demonstrate how to calculate the acceleration of an object if we're given all the forces acting on it. First, we need to discuss what mass is. Mass is the measure of how much stuff is contained in an object. And how much stuff is contained in an object, I really mean how much matter. And matter is made of protons, neutrons, and electrons. The more stuff that's contained in an object, the more mass it has. We use lowercase letter m to represent the mass of an object, and we measure mass in units of kilograms. Just to note, this is the only standard unit that we use that has a prefix. We don't use grams, we use kilograms for our standard unit. Now, mass is important because it has two properties. And the first is that objects with mass have inertia. And remember, inertia is resistance to changes in motion. So an object with more mass is harder to change how it's moving. And the second is its gravitational property. Objects that have mass experience and exert gravitational forces. The more mass it has, the more force that it would experience, or the more mass it has, the more force it would exert on other objects with mass. Now, Newton's second law is an equation, and it's an equation that states two things. The first is that the acceleration of an object is directly proportional to the net force. Okay, so if you double the net force on an object, it experiences twice the acceleration. The acceleration of an object is also inversely proportional to the object's mass. So if you apply the same net force to an object with twice the mass, you end up with half the acceleration. And combining those two statements, we get the equation that's known as Newton's second law of motion. And remember, the F net in the numerator here can be calculated separately by adding up all the forces as vectors. So now we're going to introduce the equation for the weight of an object. So remember, weight is the force of gravity that's acting on an object. So to figure out this equation, we're going to consider an object of mass m, and we're going to put that object in free fall. So if it's in free fall, our definition says that the object is only experiencing the force of gravity. It's only experiencing weight. So if we apply Newton's second law and fill in the values that we know that an object in free fall will experience an acceleration with a magnitude of g, and we know that the net force on it is equal to w, the weight. And a quick rearrangement by multiplying each side by m, we end up with this. The weight of an object is its mass times g. And remember that g has a value of 9.8 meters per second squared near Earth's surface, but we are going to use a value of g as 10 meters per second squared on positive physics. All right, so now we're going to look at some examples. Here we have a 90-kilogram teacher that's skydiving, and when his parachute opens, there's going to be a drag force of 1,200 newtons acting on the teacher. We're going to start out by drawing a free body diagram that shows all the forces acting on the teacher. So here's our teacher. Teacher will experience a force of gravity acting downwards that we will label as a W for weight. And there's going to be an upwards force caused by the drag. And we know that we draw that drag force upwards because our skydiver is moving downwards. Drag always acts opposite the velocity of an object. Part B wants us to calculate the weight of an object, and weight is equal to m times g. The mass of the object is given right here. Okay, anything in kilograms is a measure of mass. So I can multiply 90 kilograms by g. The value of g that we're using is 10 meters per second squared. And so this will give us a value of 900 kilogram meters per second squared. And remember that a kilogram meter per second squared is a Newton. So the weight of our skydiving teacher is 900 newtons. And we can now label that in our free body diagram and recall that the drag force is given as 1200 newtons. Part C wants us to calculate the net force acting on the teacher. So the net force can be found by adding up all the forces. Well, I have the drag force acting upwards, so I'll give that a positive sign. And I have the weight force acting downwards, so I'm going to add a negative W to indicate that the direction of the weight force is down. So this will be the drag force, which is 1200 newtons, minus the weight, which is 900 newtons. And so the net force acting on the skydiving teacher is going to be 300 newtons upwards. I know that the net force is directed upwards because I got a positive number. Positive forces in this case indicate upwards direction. All right, part D wants us to calculate the teacher's acceleration. Well, the acceleration can be found by taking the net force and dividing it by the mass. So this will be 300 newtons over 90 kilograms, which will give us a value of 3 meters per second squared. And again, since this net force is positive, this is a positive 3 meters per second squared, which indicates that it has a direction upwards. Now, for part E, we want to describe the teacher's speed at this time. So the teacher is moving downwards while experiencing an acceleration and net force upwards. And in this situation, when velocity and acceleration are in opposite directions, then the teacher is going to be slowing down. Let's try another example. Here we have a 50 kilogram bicyclist, and that 50 kilograms includes the person and the bicycle, is pedaling to generate a 250 Newton force. She's experiencing 100 Newtons of drag, and we're told to neglect the friction impeding her motion. So part A wants us to draw a free body diagram showing all the forces on the bicyclist. So here's our bicyclist. There's going to be the weight force, the force of gravity acting down. There's going to be an applied force forwards. That's the 250 Newton force that's described in the setup of the problem. The bicyclist is in contact with the ground, so there's going to be a normal force acting perpendicular to the surface of contact, because remember, normal means perpendicular. And then there's going to be a drag force acting backwards. We know that that drag force is acting backwards because the bicyclist has a velocity that is forward. Drag is always opposite velocity. And we know the value of the drag force is 100 newtons. So part B wants us to calculate all the forces acting on the bicyclist. So we can start with the weight force. The weight force is going to equal m times g. We're given the mass as 50 kilograms, and we know g has a value of 10. Therefore, the weight force has to have a magnitude of 500 newtons. The bicyclist does not experience any motion up or down. In the y direction, the bicyclist is at rest. For the bicyclist to be at rest in the y direction, the forces in the y direction have to be balanced. So the normal force is going to have a magnitude of 500 newtons so that it can balance the 500 newtons acting downwards, resulting in no motion vertically. For part C, we want to calculate the net force on the bicyclist. So we know that there's no motion in the y, so we don't have to worry about the forces in the y direction. The net force is going to be in the x direction, so I have to add x direction forces. So there's a forward force of applied force, and I'll give that a positive sign, and then I'll give the drag force a negative sign because that acts backwards. So the net force is going to be 250 newtons minus 100 newtons for a total of 150 newtons. Okay, part D wants us to calculate the bicyclist's acceleration. If we know the net force and the mass, then we can use Newton's second law to calculate the rate of acceleration of the bicyclist. So this is going to be 150 newtons divided by the mass, which is 50 kilograms. That works out to be 3 meters per second squared. And now part E wants us to describe what happens to the bicyclist's speed. Well, the net force is a positive number, so that means the net force is forward, which implies that the acceleration is forward. And so the velocity and acceleration are both forward. They're both in the same direction. When the velocity and acceleration are in the same direction, objects will speed up. The speed will increase with time. All right, in this example, we have an 80-kilogram man that's riding an elevator. The elevator is moving downwards with a speed that's decreasing at 3 meters per second squared. So we need to use that information to determine the direction of some of these vectors. It says that the elevator is moving downwards, so we know the velocity vector is downwards, but it says that the speed is decreasing. So if the speed is decreasing, that implies that the acceleration is up, because an object that's slowing down or decelerating has to have an acceleration and velocity that are in opposite directions. An acceleration that is up also implies that we have a net force acting on the man that is up. Part A wants us to draw a free body diagram to show the forces acting on the man. So here's the man, and he will experience a gravitational force that acts downwards, known as weight. He is in contact with a surface, namely the scale, that will exert a force perpendicular to the surface and away from the surface. And in this case, that would be upwards. So there's a normal force exerted by the scale acting upwards. Part B wants us to calculate the net force acting on the man. So to do this, we're going to use Newton's second law. Newton's second law says acceleration is net force divided by the mass. And I know what the acceleration is, I know what the mass is, so I can calculate the net force from this. The acceleration is given as 3. The mass is given as 80. And so the net force is going to be 80 times 3, which works out to be 240 newtons. And again, that 240 newtons is upwards, so we're going to give that a positive sign to keep track of our directions. Now, for part C, we want to figure out what the scale is going to read. And the scale will read what normal force it's exerting on the man. So we can calculate what the net force is by adding up all the forces acting on the man. It'll be the normal force minus the weight force. Normal force gets a positive sign because it's acting upwards, and the weight gets a negative sign because it's acting downwards. So I know the net force is a positive 240 because that is upwards. We're trying to determine the normal force, so I'm solving for n, and I know the weight is going to be 800. I know the weight is 800 because I can take the mass of the man and multiply it by g, or 80 kilograms times 10 meters per second squared. That's how I know that the weight is 800 newtons. So the normal force is going to be 240 plus 800, which is 1,040 newtons upwards. Okay, last example for the unit. Here we have a 60-kilogram bicyclist, and that mass includes the bicycle's mass as well. that's just coasting. And so that implies there's no applied force pushing forward. She experiences an 80 Newton drag force and a 40 Newton friction force. Part A wants us to draw a free body diagram to show all the forces acting on the bicyclist. So here's our bicyclist. She's going to experience a force of gravity that acts downwards, a drag force that acts backwards, and we know that the drag force acts backwards because she's moving forwards. A frictional force will also act backwards, and we'll have a normal force that acts normal or perpendicular to the surface of contact. Part B wants us to calculate all the forces acting on the bicycle. So we're going to start with the weight force. Weight is equal to m times g. We're given the mass of the bicyclist as 60 kilograms. We're going to multiply that by 10 for g, and that gets us 600 newtons. So the weight force is 600 newtons. The frictional force that was given to us, that's 40 newtons. The drag force was also given to us, that was 80 newtons. And we can infer what the normal force is going to be because there's no motion in the vertical direction. If there's no motion in the vertical direction, vertical forces have to be balanced. So if there's 600 newtons acting downwards, there's 600 newtons acting upwards. Part C wants us to calculate the net force on the bicycle. So we can calculate the net force on the bicyclist by adding up all the forces. In this case, we have a drag force and a frictional force that are going to be unbalanced. I don't have to worry about the normal force and the weight because they balance and cancel each other out. So the net force is going to be the drag force plus the friction force, or 80 plus 40, or 120 newtons. Okay. In part D, we want to calculate the acceleration. So the acceleration is going to be the net force divided by the mass, and I know both of those numbers. It's 120 newtons divided by 60 kilograms, and that gives a value of 2 meters per second squared. Okay, and for part E, here we said if the bicyclist starts coasting when moving at 10 meters per second. Well, 10 meters per second, that's a kinematics quantity. That's the things that we studied when we were talking about motion. And in this case, that's the initial velocity. It asks us about a distance. Distance is delta x. And then it says that she's going to come to rest. We want to know the distance to come to rest. Well, at rest implies that she's going to have a final velocity of 0. This is a kinematics problem. I do this at the end because I want to point out that there's a connection between motion that we've been studying all year so far to force stuff. And the link between the force stuff and the motion stuff is acceleration. There's acceleration in Newton's second law, and there's acceleration in most of our UAM equations. And so we now just need to find a UAM equation with final velocity, initial velocity, delta x, and acceleration. And we have that. Okay, the final velocity is 0. The initial velocity is 10. The acceleration is 2, but we got to be careful. I'm going to put that in as a negative number because the acceleration is going to be backwards, right? The net force is 120 newtons backwards, opposite motion, times delta x. And now we just need to crunch the numbers. 0 squared is 0. 10 squared is 100. And here I get negative 4 delta x. Well, I think we can do the math from here. delta x has to be 25 meters.